you have the ecosystem services you need, but it's very high tech. And we use all the technological nous we have and bring it to bear on these problems. Again, you can see elements of that. So these are the ways we can envision the future you might live in. Different value systems, different technologies, different approaches to how we deal with society environment problems. Well, where are we going? Well, if you take a business as usual, which has stronger elements of those first two scenarios than the second two, this is where we're going. This is a very famous image, the so-called night lights of Earth. It's a composite image done by NASA, the US Space Agency. So if the Earth were nighttime everywhere at the same time, that's what it would look like. This is an exceptionally good indicator for energy use. So you see, where's the Earth lit up? Eastern United States, Western Europe, and Japan. Those are the three big areas of energy use. And if you look at Australia, you can just make out the capital cities there. But now let's try to put that in the context of the graph I started with, the ice core data. Again, this shows the natural variability of the Earth's climate. It's highly variable climate, but notice that it has limits. Notice that temperature never drops below a critical value, and it never rises above a critical value. And the same with carbon dioxide. If you want an analogy, just think of your own blood pressure and heartbeat. Your heartbeat has a regularity, like that, and your blood pressure sits within normal limits. If your blood pressure goes really high, your doctor gets worried, and something has to be done about it, or your health will suffer. Same thing that goes too low. And the Earth is very much like that in some respects. This is one of the reasons that prompted James Lovelock to use the term Gaia to define the Earth as a living organism. Because at the system level, at the planetary level, it does show features of a living organism. But now let's put this human perturbation on. This is the measured carbon dioxide in the atmosphere that we see now. We measure it, we have good instruments. It actually now stands above 380. This slide is somewhat out of date. It's well above 360. Now, if you take the ice core CO2 record, and here I've used broken lines to indicate the upper and lower bounds, just like normal blood pressure, this would be from here to here. Now, you go into the doctor and he measures your blood pressure, and your blood pressure's up there. You'll be in hospital very quickly. All right, but this is where the planet is. This is CO2 now. And this extra bit above this broken line is what has been added by humans in under 200 years, which is a very short time frame compared to hundreds of thousands of years. So this is a very big change in terms of how the planet operates. And you might say, because there's a link between temperature and CO2, we should see that in temperature, and we do. Here's a temperature record. This is Northern Hemisphere, because the data is much better there. And again, this yellow line shows natural variability, and these blue bars are the errors in those measurements, because until we had thermometers, which is where this black starts, we had to estimate it from tree rings and techniques like that. But again, look at just as CO2 is going up, look at what temperature is doing. The X is about where we are now. Okay? But if you look at those black lines, look at you have cold years still, cold years, and warm years. So if you've seen the blogs over the last week or two about global cooling, they're just picking up a fraction of one of those black bars that may be a little bit low. So don't mistake variability with an underlying trend. And you can see that over 150 years we have a quite strong underlying trend toward warmer temperatures. But it's an absolute no-brainer when you look at what's happening to the atmospheric composition. Okay, now let's go into the future. And here we've taken these night lights images that I showed you, we've digitized them so we can have a good play with them. So it's exactly the same NASA image that I showed you a few minutes ago. But now what we can do is we can put an energy scenario on top of that. So what we've done is taken a fossil fuel intensive energy scenario, so-called business as usual, and the assumption here is the world doesn't get its act together. We keep burning coal, we use the rest of the petroleum, etc. And we keep growing economically and using a lot of energy without worrying about efficiency and so on. And then we simulate the night light. So watch what happens. This is going to be around 2070 or 2080. We go into the future and watch how the Earth lights up. There we go. So if we don't do anything, that's where the human enterprise is going in the year 2070. Now you'll obviously notice that India and China are lighting up a lot more. And you hear a lot of people worried, well, it's India and China's the problem. But if you actually were careful, or if you notice carefully here, the US is lit up a lot more, Western Europe is lit up a lot more, and so is Japan. So it really is a global problem. By the way, those of you who are worried about equity issues too, which is a hugely important issue, notice how unequal in a business as usual world the world actually stays. There are large numbers of people here, and there's virtually no change in energy usage from what it was in 2000. So the big equity issues also. But anyway, if you look at this in aggregate, you can then calculate what is the carbon dioxide that that energy footprint actually emits, and then you can run that through a climate model. And that's what you get. This is that same graph I showed you of the natural variability of climate. This X is where we are now. You recognize that rise over the last century and a half. So there's where we are. We're approaching about 0.8 of a degree above the pre-industrial global mean temperature. That orange bar are the climate model projections for the year 2100 that were published by the IPCC. Now they range from about 1.5 degrees up to close to 6 degrees by the end of the century. Now the image I just showed you of the energy pattern in 2070 would put you up around 4 degrees. So that's a pretty strong scenario. Where are we now? Well, first of all, even if we could cut emissions to zero tomorrow, we'd still be close to 1.5 degrees because of the momentum in the climate system. You can't turn around the climate system tomorrow. It's like taking a big battleship. You can shut off the engine of that battleship if it's steaming at 25 knots, and it won't stop the next day or the next hour. It's got some momentum in it. So does the climate system. By the time we hit 2 degrees, what will the impact be? We'll have very large biodiversity losses. And the best estimates we have will be that things like the coral reefs will disappear, polar bears will be gone, and so on. There's a good reason for the coral reefs. The ocean will be a lot more acidic with a lot more CO2 in the atmosphere. It dissolves in the ocean, forms carbonic acid, and it makes it much more difficult for reef organisms to form their shells. So the bleaching events we've seen will be compounded by the fact it's more acidic. So we're going to lose reefs and probably a lot more biodiversity because these are the most vulnerable systems. They can't adapt, at least not at the speed at which they need to adapt. By the time we hit 2.5 to 3, we're probably committed to losing the Greenland ice sheet. That was the thing I was talking to you about earlier. That's equivalent to 6 meters or so of sea level rise. There's now concern about the West Antarctic ice sheet, which is also showing some instability, although not as much as Greenland. That adds about another 5 or 6 meters of sea level rise. So if Greenland and West Antarctic went, that's about 12, 13 meters of sea level rise. That's quite significant. Question?
I saw a headline somewhere that the Greenland, that actually some scientists think that the Greenland ice sheet only not because of global warming, but because of the Earth's geothermal heat.
Well, that geothermal heat doesn't change very much through time. There's geothermal heat. Why is it happening just now? Because we see very big changes over the last decade or so. And all through the current warm period, which is 12,000 years of the Holocene, we haven't seen any change in the Greenland ice sheet. It's only been in the last several decades that we start to see movement. So you would not expect a flux of geothermal heat to change that fast. So I would say that may be a nice headline in the media, but I don't think it's going to stand up when you look at the science. Okay, so getting back to this, by the time we hit 4 degrees or so, we're going to have a lot more impacts on human systems, on agriculture, on built infrastructure, on human health, and so on. It'll make it much more difficult. By the time we hit 5 or 6, I think it's likely that modern civilization won't be able to handle that if it happens within a century. That's just too fast for the ecosystems on which we depend for all sorts of services to adapt. They won't be able to adapt. I don't think we'll be able to adapt either. So this is the argument you're seeing in the politics and in the media now, is how fast should we mitigate? How much should we allow this curve to go up, and how much should we try to turn it around? Just to show you how urgent it is, this is the CO2 emission trajectory. These are the sorts of changes we need to make over the next century to bring CO2 down to levels at which you would limit climate to about 2 degrees. That's about a 2 degree scenario, 3 degrees, 4 degrees. The black line is where we're going now. So this part of the graph, if you blow it up, looks like this.